Have a textbook? Good. You can follow the textbook. I forgot to bring mine. Anyway, it's the same. Okay, those of you have this notes, you print out or you want to follow the polymer notes. Okay, exactly what I'm going to do is I'm going to do the chapter 1, which is the first topic. And this first topic is nothing new because this is what you learn from Dr. Chiu. Okay, what I'm going to do tonight, only tonight, is to revise, refresh your memory, to prepare for the coming chapter. Okay, so refresh your memory. So what I'm going to refresh is really the thermodynamic parts. So what you understand in the thermodynamic system, I'm going to do a quick revision and do some tutorial. Okay, so please understand what is the meaning of closed system, open system, and sign convention. When you do comparison of heat work done, a lot of students make a mistake on the positive and negative. So how to know what is positive, what is negative? Okay, this is important. This is what you learn from Dr. Chiu. So I need to do some quick revise. Yeah, then all these properties, thermodynamic properties, what are there? For example, enthalpy, internal energy, all this. I'll talk about this also, and what is the unit for these properties. Then you learn from Dr. Chiu also, first law of thermodynamics. How many of you still can remember? I don't know, let's do it one more time. Then perfect gas, what is perfect gas? What's the meaning of perfect gas? Then you also learn PV diagram. What is PV? I will talk about this. Steam table, very important. How to apply the steam table? How to apply this? Okay, you learn already. After 3 weeks, 4 weeks holiday, come back. I don't know how many of you still can remember how to use the steam table. Okay, then this basic property of fluid, this one I will do it in chapter 6 later on. I will do it something like 5 weeks later. Why? Because I find that if I do it now, in tonight, 5 weeks later when I cover chapter 6, I think you will mostly forget it. So then again need to revise. So that's why this part I will do it later. Okay, first of all, what's the meaning of system? Okay, when we say thermodynamic system, this thermodynamic system refer to what? What does it refer to? Okay, example, air compressor. So does it mean air compressor? No. When we do calculation, remember under Dr. Chiu, when you calculate like PV equal to MRT, what are you calculating? You're actually calculating only the gas. You're only calculating the gas, like air, like water, like steam. The water, steam, air, these are the system. So this system doesn't refer to the compressor, not the mechanical part. We are talking only the gas or the fluid inside. Okay, this is something that we are calculating. Because when we do calculation, we only calculate this one only. Okay, if you say why not calculating this? Yes, after this one is mastered, then you expand to other mechanical parts. But it's not under thermodynamic anymore. It's a system. It's a complete system, mechanical engineering system. It's not just thermodynamic system. Okay, steam turbine, steam engine. So this is the system. These are system refer to the fluid. So the fluid the system are enclosed by a boundary. Enclosed by a boundary. So the energy can cross the boundary. Energy can cross the boundary. So energy in the form of heat or work done can cross the boundary. So this boundary can be real or can be imaginary. Real is what? Something that you can see. For example, like this one. For example, I have this container. So this container is real. You can see it's a container. Then inside got water. So means this is the boundary of this water inside, and the water inside is the system, my system. If I heat up the water, and this is fully tightened, what happens? Water will boil. Then the pressure inside increase. So means the water subject to heating, something happens inside. But the boundary is real. You can see it's the energy in the form of heat cross the boundary and heat up with water. But no work done because the boundary is fixed. Okay, so boundary can be real or imaginary. Imaginary means what? You cannot really see. Okay, what do I mean? You cannot really see. Okay, example. Better illustrate with example. This is something that you can easily see. Car engine. Okay, something like this. You have a car engine where you have piston, you have cylinder wall, you have the cylinder head. Where the cylinder head you have the bar and the spark plug. Okay, all these things when the bar closed, this is become a closed system. The gas enclosed inside the closed system. So this boundary you can see, you can easily identify, oh, this piston top, this is a side wall, this is the bar plate. So this encloses the air inside. Okay, when you have the air subject to heating, then this air temperature will increase, the pressure increase, you will do work. Okay, then you do work by expanding, and the work is so-called transfer across the boundary. So something like you push the piston down, so it transfers the boundary and cause the crankshaft to run. So you have heat, energy can cross the boundary. You have the work also can cross the boundary. So this is the system. The system refers to this air here. This is the boundary. So this is something you can see. So you can easily identify. This one will be difficult already. This is what? This is the steam turbine. Okay, you look at the steam turbine, you say, okay, where is the boundary? Can I say there's a wall? Cannot identify the wall. So if you put the turbine this way, this one is from small to big. From small to big. So this row of turbine rig is something like that. You cannot easily identify a clear boundary. Therefore, we have to imagine there's a boundary like that. Imagine there's a boundary like that. Where the steam coming in, expand inside the turbine, cause the turbine to run. When the turbine runs, means what? It produces work done. So the work done cross the boundary, this imaginary boundary. Then the steam after expand go up from the other end. Steam coming out. So this is the imaginary boundary. Cannot really see, but you imagine, oh, there's a boundary like that. Something like that. Okay, so what is the meaning of closed system and open system? This is a very good example. You see this car engine, this air trapped inside. If the bar is all closed, means the air trapped inside cannot go up or air cannot come in. So this air at this point of time is the closed system. This steam, you have the steam coming in, expand inside the turbine, after expansion go up. So you have flow coming in, flow going up. This will be an open system. Okay, closed system means the air cannot come in or the fluid cannot come in. Only energy transfer can cross the boundary. Energy transfer means what? Like this case, heat can cross the boundary. Work can cross the boundary. So only heat and work can cross the boundary. So you heat up the air, cylinder expand, produce work done. So this heat and work can cross the boundary. For open system, not only energy can cross the boundary, the mass also cross the boundary. Like just now the turbine. You have steam coming in, expand, cause the turbine to run, then you have steam after expansion going up. So that's why you have mass in, mass out. Very clear cut is when you see this mass flowing in, mass flowing out, that definitely is an open system. If you do not see any mass flow, this is enclosed, then this is the closed system. Sign convention, this is important, at least for chapter 1 and chapter 2, because we're going to use this very often for chapter 1 and chapter 2. When we say heat supply, then this number, for example, heat supply is 50 kilojoule. Then this 50, when it comes to calculation, is positive number. We put positive 50 kilojoule. If we say heat reject from the system, 50 kilojoule, cooling, heat reject. Then, because heat reject, we have to put the negative. Let's say 50 kilojoules, so we have to put minus 50 kilojoules. Minus 50 because it's a heat reject, which is the cooling effect. Then same for the work done. But work done is like that. If you have good input, for example, I use my hand compress the bicycle tires pump, the bicycle tire pump, I press. I use my own body energy and input and so-called compressed air. So this more input due to my energy will be a negative energy. Means I input the energy to the system. So the energy come from me, lose out from me and go into the system. So it's a negative figure. So if let's say the work is come out from the system, let's say something expand and push and cause work to do produce work, then this work output is a positive number. Okay, thermodynamic properties. Okay, let me ask you what is the unit for pressure? Pascal, very good. Any other question? Newton per meter square. Yes, very good. Okay, bar, Newton per meter square or Pascal? Now my question is, bar and Newton per meter square, what's the relationship? Sorry? 10 to the power 5. Yes, very good. 10 to the power 5. Okay, so 1 bar is 10 to the power 5 Newton per meter square or Pascal. If you convert to kilo Pascal or kilonewton per meter square, just take away 3 0 from here. So 10 to the power 5 means 5 0. Take away 3, you left 2. So you left 2 0 here. So next, what's the unit for volume? Anyone still don't know what's the unit for volume? So sometimes we use liter. Okay, because especially for engine, we like to use liter. Especially when you buy motorbike or buy car, or you not only car or engine, sometimes compressor also. So sometimes you like to use this unit in terms of liters. So how to convert liters and meter cube? So we know that 1 meter cube is equivalent to 1,000 liters. So what does it mean? So 1 meter cube is how big? Very easy. Just take 1 meter by 1 meter by 1 meter depth. That enclosure is exactly 1 meter cube. And you need to buy 1,000 liters of Coca-Cola pour inside in order to fill it up. So that is 1 meter cube. Okay, so 1 liter is equal to 1 divided by 1,000. So you have 1 to the 10 to the power minus 3 meter cube, or 0.001 meter cube. So 1000 cc is equal to 1 liter. So most of you know 1000 cc. Temperature. So most of the time we use degree C. So in thermodynamics, sometimes we use Kelvin. So how to convert from degree C to Kelvin? Plus 273. Very good. Plus 273. Okay. Very good. Most of you still can remember. Okay, now come to something more challenging. Not very difficult, but challenging. Internal energy. Okay, what you say is correct. But the thing is, if you talk about energy, usually the unit is joule or kilojoule. But what you just mentioned is specific unit, specific energy. For example, I give you a moment. Specific quantity. So you are talking about per kilogram of mass. Per kilogram mass. Meaning we say the unit, the energy divided by the mass. So let's say specific volume. Specific volume means you use the volume divided by the mass. Okay, this M here is not meter. This M here is the mass. Okay, for example, I have 2 meter cube. My total mass is 0.2 kilogram. So I use 2 divided by 0.2, I get my specific volume, which is 10 meter cube per kilogram. So means every kilogram of this fluid, the volume is 10 meter cube every kilogram. Okay, the same as the internal energy. Yeah? So internal energy, if let's say you're talking about specific internal energy, you'll be the internal energy divided by the total mass. So for example, I have 200 joules and my mass is 0.2 kilogram. So my specific internal energy is equal to 200 divided by 0.2. So equal to 1 kilojoule per kilogram. Okay, take note, you look at these figures, this character. When I say specific, you notice the character I use small letters, not the capital letters. So capital letters normally refer to the total energy, the absolute energy in kilojoules. When we talk about specific quantities, we normally use the small letters. Okay, we normally use the small letters. So the same also apply for specific enthalpy. So specific enthalpy is the enthalpy divided by the total mass. You're open for your credit. Okay. Normally, I don't know. Nowadays, what time is the canteen close? 8 o'clock. I think I better let you go now. So you go for a break. How long you need? 20, 30 minutes? Sorry? 30 minutes. Okay, you go for a break, 30 minutes. Something like 7:55, come back, can? Yeah, before the canteen close. But can be converted from one form to another form. So means the energy can be transformed from heat energy to work done, or from heat energy to the internal energy, or closed system. If let's say open system, you have more type of energy. So I'm only talking about closed system. There are only 3 types of energy, which is the heat, work done, and the change of internal energy. So for closed system, we only have these 3 types of energy. So I'm talking about if you have a heat supply, or you have a heat reject, you have a work input, or you have a work output, then something changes in the internal energy. Okay, sometimes for constant temperature process, you don't have any change of internal energy, then this work done is equal to the heat transfer. Okay, this is based on the closed system. The first law of thermodynamics, the energy equation is this. And this equation we call non-flow energy equation. Non-flow energy equation. So NFEE. So this is what you learned before for closed system. If let's say this is for open system, then you have more energy to deal with. So what are the energy? So beside the heat and work done, we have to deal with the enthalpy. This H is the enthalpy. Okay, so this is the change in enthalpy here. Then this half m C2 square minus C1 square. Why is this? This is something to do with the velocity. So let's say the flow coming in at this velocity C1, going out at this velocity C2. So there's a change in the velocity, so there will be some change in the kinetic energy. Velocity is related to the kinetic energy. So if there's a change in height from higher location flow to a lower location, so there's a change in height. This change in height will be resulting in this, which is the change in the potential energy. So this Z refer to the height, the change in height, Z2 minus Z1. So if everything divided by n, everything divided by n. Everything divided by n, we get this equation, Q minus W equal to H2 minus H1. So the n will disappear here, this n also disappear. So you look at this one, how come this one becomes small h? Because divided by n. This divided by n becomes small q. This W divided by n becomes small w. Okay, so this equation in short we call steady flow energy equation. Steady flow energy equation. Right. Anyone hasn't signed your attendance? Okay, so steady flow energy equation. So when you see question like this, open, when you have a closed system, then you apply the closed system energy equation. When you deal with open system, then you use the open system energy equation. This one is for open system. Sometimes we call this steady flow process or flow process in short. Sometimes we just call it flow process. Okay, take note. You may wonder what happened to the internal energy. What happened to the internal energy? How come here don't have? Okay, the internal energy is part of the enthalpy here. Remember, enthalpy H is equal to internal energy plus the pressure times volume. So this internal energy is part of the enthalpy inside. Okay, perfect gas equation. This is very often that you need to use perfect gas equation. The first one you use is PV equal to MRT. Okay, perfect gas. So what do I mean perfect gas? Like air, like nitrogen, oxygen, air, all this you can consider as perfect gas for ease of calculation. So if steam is not perfect gas, so you cannot apply this for calculating steam. Because steam, we do not consider steam as a perfect gas. So it means you cannot use this one for steam. Okay, so very often than not, we use this one to calculate the mass. But we cannot use this one for steam, only for gas, like nitrogen, oxygen, or carbon dioxide. Anyone use carbon dioxide in your industry? For welding? Very good, yes. Last time, welding used a lot of carbon dioxide, in case you're not aware. Because carbon dioxide is a very good inert gas for certain type of welding process. So that welding we call CO2 welding. Okay? But sometimes they use another type of gas. But CO2 is the common gas used for welding. Okay, so this one, the equation, if I take away R, by the way, what's the meaning of R? Anyone want to make a guess? What is the R? What's R representing? Gas constant, yes. It's the characteristic gas constant for a particular gas. So for air is 0.287 kilojoule per kilogram K. Okay, for air. For other kind of gas, the figure may change, may not be the same. So this 0.287 is only applied for air. So if I do this, I take away R because these two sides are the same. So notice the common term is what? P1 V1 over T1 equal to P2 V2 over T2. So become this equation. And in short, we call this PV over T equal to constant. Because P1 V1 over T1 equal to P2 V2 over T2. If you have another 0.3, then you have P3 V3 over T3, and so on. So in short, we call PV over T is equal to C, means constant. So this is for perfect gas. Another one you seldom use one is Cp minus Cv equal to R, which is this R here. Now my question is, what is Cp and what is Cv? Yes, constant pressure, constant volume. So this constant pressure, constant volume for what? Which is the specific heat capacity for constant pressure. And this is specific heat capacity for constant volume. If you use Cp divided by Cv, you get gamma. So this is fixed. This divided by this always equal to gamma. So question is, what is gamma? You still can remember what is gamma? Anyone? Adiabatic, very good. Adiabatic index, yes. Adiabatic index. Okay, what is adiabatic index? I'll show you in a moment. Okay, PV diagram, very important. PV diagram. You need to learn, you need to recall. You learned before, it's not new. You need to recall. What is PV diagram? PV diagram stands for pressure volume diagram. Pressure volume diagram. So when I plot a PV diagram for a process like this, which is a constant pressure process, For example, inside this cylinder, I have this amount of air subject to heating. So what happens when subject to heating, the pressure will, because the pressure inside and outside is constant, so the volume will expand. So you will have a constant pressure expansion. So when you want to plot this constant pressure expansion in the PV diagram, how does it look like? Constant pressure means pressure no change, so you only have a horizontal line. Constant pressure from one point expand to another point. Constant pressure expansion. From one volume expand to another volume. So if you contract it, contract means you lose it, then the pressure will drop. Actually, it's the contraction because constant pressure process. So you contract at the constant volume, constant pressure. So go back to the original volume. So this is a constant pressure, so horizontal line. How about constant volume? Constant volume, one very good example is the pressure vessel. So pressure vessel, I just have the fire extinguisher here. I think it's off somewhere. Last time it's outside. Fire extinguisher, the cylinder is a very good example. It's a rigid vessel. So let's say I have this container of air subject to heating, and this volume is fixed. Let's say it's 1 meter cube. So no matter what happens, the volume always fixed. So fixed volume is what? The volume is a fixed reading, so you have a constant volume process, so it's a vertical line. So of this volume, let's say 1 meter cube, and this pressure, let's say 1 bar. You heat up the volume, the pressure increases. Because the volume is fixed, so the pressure will increase. So if you cool it down, the pressure will drop. When you cool it down, you lose heat, the pressure will drop. But the volume remains the same. So this is a constant volume process, it's a vertical line. So just now, constant pressure, horizontal line, this one, constant volume, vertical line. How about polytropic, adiabatic, and isothermal? Okay, all these processes look something like this. If let's say you have a polytropic, adiabatic, or isothermal compression, you will have a curve. If you have a polytropic, adiabatic, or isothermal expansion, again you also have a curve. But then you may say all these three look the same. I will say all these three processes are curved, but the gradient of the curve is different. Exactly how different, I will show you later. I will show you later. Especially come to chapter 5, air compressor. I'll explain that. So this curve, there's an equation for this. The equation is PV equal to C. If this is isothermal process, then it's PV equal to C. If this is polytropic, then it's PVN equal to C. If this is adiabatic, just now we said about adiabatic index. PV instead of N now become gamma. So PV gamma equal to C. So this gamma for this thermofluid power, we use fixed value 1.4. So if you ask me, is it always 1.4? I would say roughly that. Okay, but it's not really fixed. It changed a bit. It varied a bit. But for easy calculation, let's keep it at this value 1.4 for air. So for other gas, let's say you are looking, for example, some of you use nitrogen. Some companies use liquid nitrogen. Then this liquid nitrogen evaporate, become gas nitrogen. The properties is different also. The gamma or pure nitrogen is different. Slightly different. It's not really 1.4. This table is very important. You must know how to apply. It's given to you, but if you for this thing, but you don't know how to apply, useless. So you must understand how to apply this. So how to apply? Very simple. You must first of all identify the process you are looking on. Process means what? Okay, for example, like this case, this is a compression process. this from 1 to 2 is one process. So this is one process. Let's say this is polytropic, then you look at polytropic. If this is adiabatic, look at adiabatic. So now you have this expansion, is another process. So this is another process. This is one single process. So once you identify the process, then you look at this column. If you are working on constant pressure, just look at constant pressure column. If you are working on constant volume, just look at this column. If you are working on isothermal, constant temperature, just look at this column, constant temperature column. If you are working on polytropic, look at this column. If you are working on adiabatic, just look at this column. So what do I mean is, you just look at here, other no need to see. So look inside for one. Okay, if you are working on pressure, temperature, volume, these three items, these three properties, look at the equation of state. Okay, these three properties: pressure, volume, temperature. Temperature must be in Kelvin, very important. Please convert your temperature to Kelvin first before you do your calculation. Always remember to do that. Then the next row, delta U. This delta, the triangle is a delta. What does it mean? It means change. Change of what? Change of internal energy. Change of internal energy. So you can see that the change of internal energy calculation is always the same. It's mCv T2 minus T1. However, this one is 0. Why this one is 0? Want to make a guess? Yeah, temperature is the same. T2 and T1 is the same. So becomes 0. That's the reason. Okay, very good. Next, W. W is work done. So work done, calculation depends on what process you are working on, so the equation is also quite different. Quite different. So, but you notice that the work done for constant volume process is 0. Okay, what does it mean? If you have no change in physical volume, the volume always constant, you will not have mechanical work done. We are talking about mechanical work done here. So if you have no constant, you have constant process, constant volume process, you have no change in volume, you will not have any mechanical work done. Next column we are talking about Q. Q is the heat transfer. Heat transfer. Okay, heat transfer constant pressure. That's why just now I mentioned specific heat capacity for constant pressure. If you are working on constant volume, this C becomes CD, specific heat for constant volume. If this is constant temperature process, the change of internal energy is 0, then the heat transfer is equal to work done. Then for polytropic is delta U plus W. For adiabatic, there is no heat transfer. That's why you see 0 here. Adiabatic. Then how about this row? This row, I will talk about this in chapter 2. Okay, so this one we're going to learn soon. This row. So there's a new delta S we're going to learn in chapter 2. Okay, this one very quickly, I just go over, give you some introduction. But you cannot understand, never mind, I will talk about this one more time when you come to chapter 3. So this is something that, based on what you learn, based on the thermodynamic system, where you have a fluid undergoes a series of processes. What do I mean series of processes? Just now I said one single process, this is one single process, and you have another process after that, then you have another process, continue until it finally returns to the initial state. Means after once the complete cycle, it comes back to the original point. For example, I show you this one example is the car engine cycle. This is auto cycle that you're going to learn. So this is one single process. So the piston move one stroke is one process here. Then you have the heat supply. Then you have the expansion where the piston move and produce the work done. So this is another process. Then finally you have another process here, which is to lose heat. So you have 4 processes: 1, 2, 3, then back to 1. So now come back to 1. Come back to original point, the initial point. So when we want to calculate the energy equation for these 4 processes, what do we use? Because this is a closed system, So we apply the non-flow energy equation. Non-flow energy equation to all the 4 processes. Means from 1 to 2, 2 to 3, 3 to 4, 4 back to 1. So when we apply that, so what do we have? So we will have sum of the heat minus sum of the cool down equal to sum of the change of internal energy. So it's a very long equation, but never mind. Don't worry. More important is this one. The right hand side, you have the negative U1 here, you have the positive U1 here. You also have a positive U2 here, then you have a negative U2 here. Likewise for U3, positive, negative, U4, positive, negative. So all this you can cancel away. So what do you have? End up you only have Q and W. You only have Q and W. Means the sum of Q equal to the sum of W. So what does it mean? Means the net heat is equal to the net work. Okay? This is the concept later on you're going to apply in your chapter 3. So if you don't quite understand, don't worry, I'll do the explanation again when we come to chapter 3. It's still based on this thermodynamic cycles. Okay, based on first law of thermodynamics. Okay, now let's do some examples. Practice it, yeah. Okay, when we come to practice, normally what I like to do is I will use a whiteboard. I will show you the question. I'll try 1 or 2 questions. Okay, this is chapter 1, so I how to say, just warm you up. You don't have to submit, but just warm you up. So chapter 2 onward, just like I mentioned before, you need to submit, right? You need to submit starting from chapter 2. Okay, so chapter 1 only let you try after this. So this is what normally I will do. I will do some examples using the tutorial question, but I will not base exactly the same question here. Why? If I base on exactly the same question and I get this answer, you just copy. Then after that, will you do the same question again? Unlikely. So you just copy, finish. Then just sit and wait for me to do the next one. Then would you learn anything? Maybe, but maybe not also. So to make sure you learn, pick up something, at least you understand. What I will do is, this same question, let's say the one I'm going to try out, I will change the number. For instance, this question 1. A rigid vessel contains 0.5, instead of 0.1, I change to 0.5 meter cube of air at a pressure of 5 bar. Instead of 5 bar, I change to okay, instead of 5 bar, I change to 10 bar. 10 bar. Okay, change to 10 bar. And the temperature, instead of 200 degrees C, I change to 227. Easy for me. 227 degrees C. Okay, 227. Then what happens if the vessel is heat? This is rigid vessel, remember. Rigid vessel means what? Volume is constant. Cannot change because the volume of the vessel is rigid. So it's constant volume. So now it's heated to a temperature of 250. I change this to 327 degrees C. Increase by 100 degrees. So calculate the final pressure and the heat supply. Calculate the final pressure and the supply. So I'm going to base on this number. Show you how I do the working. Later on, you base on the same question, but the original number. You do the question again, you should get this answer. Because I changed already, so my answer will be different. But at least I show you the working. Okay, so based on this question, okay, let me write down what's the question. So this is the constant volume process. Question 1. Constant volume process. Now the initial volume and the final volume is the same. This is 0.5 meter cube. This is constant volume, so volume no change, 0.5 meter cube. Initial pressure is 5 bar, 10 bar, sorry. I think to 10 okay. Initial pressure is 10 bar. And temperature is 227 degrees C. 227. Why I choose 227? Easy for me. Convert to Kelvin plus 273. Exactly 500 Kelvin. Exactly 500 Kelvin. So this is 0.1. Now heat up to 0.2. 327 degrees C. Same thing, you plus 273. This is 600 Kelvin. Now heat up to 327 degrees C. Calculate the final pressure. Is this P2? What is this P2 here? Calculate the final pressure and the heat supply. Q. Okay, to do that, let's look at what we have. So now we are working on constant volume process. So which column are we working? This constant volume. So if we want to calculate pressure, use the first row here. Equation of state. So first row, what do we have? Sorry, this black mark is actually covered by buildings. Okay, so constant volume. If I want to find P2, I use this first row here, so I have P1 over T1 equal to P2 over T2. I use this equation to find my P2. Okay, I use this one to find my P2. Okay, my only unknown is P2. This is the only unknown. Okay, I want to find my P2. So what do I do? Let's do some shifting of the equation. I transfer the T2 from the right side to the left side. From the right side to the left side. So become multiply. So it's P1 times T2 over T1. Why multiply? Simple. This, if you cannot understand this, just remember this concept. 8 divided by 2 is equal to 16 divided by 4. Correct? So I shift my 4 to the left side. What do I have? So 8 times 4 divided by 2. Cannot be divided. 8 divided by 4, 4 sure also divide wrong. You can't get the same number, 16 here. So you use this simple method to confirm your manipulation. So T2 shift to the left side become multiply. So now I can use this one to find my P2 here. So my P2 is equal to P1 10 bar, 10. Okay, now question. 10 bar, this is bar. Do I need to convert to kilopascal or Newton per meter square or kilonewton per meter square? Up to you. Okay, let me show you. Now I still leave it as 10 bar. The pressure unit is bar. Okay, times T2, 600 over T1, 500. So this 600 divided by 500 is 1.2. 1.2 times 10, 12. So what's the unit here? Bar. Bar, yes, very good. Bar. Why bar? Because this one just now earlier I put this bar here. That's why my answer will be in bar. Very good. Okay, so this one no need. Pull up. Next, heat transfer, Q. Okay, heat transfer for constant heat transfer for constant volume is mCv T2 minus T1. mCv T2 minus T1. So in case you ask me, what is the exactly below what's the value of Cp, Cp, all these are given. Okay, all these are given. So let me write here. I put here. Q equal to mCv T2 minus T1. Okay, let's see what we have. Cv given, so this one no issue. T2 given also. T1 given also. M don't have. How to find M? I don't have M. Very good. PV equal to MRT. So now we want to find M. We use the perfect gas equation. Perfect gas. So perfect gas equation says that pressure times volume is equal to mass times R, which is the specific, the characteristic gas constant times temperature in Kelvin. So now, if I look up this mass from point 1, everything I have to use point 1. I use P1, I use V1, I use T1. If I work on the point 2, everything will be based on point 2. Cannot mix. You cannot say P1, V1, but I only have T2, so I put T2. Cannot mix one. Must be of the same point. Okay, very important. Okay, so now I'm based on point 1. So everything comes from point 1. T1, V1, V1. Okay, P1 is 10 bar. Now I want to talk about the unit here already. I want to talk about unit. Okay, let's talk about R first. The R unit is in kilojoule per kilogram. Okay, and R is 0.287. The unit is in kilojoule per kilogram. So take note, this is in kilojoule. This is in kilojoule. I highlight this one first. Kilojoule per kilogram K. Then temperature definitely is Kelvin. 1 Kelvin. Okay, this one no issue, the right side. Okay, now talk about left side. Volume definitely is meter cube. Meter cube 0.5. Now the pressure. You put bar, you put Pascal, or you put kilopascal? How many of you say Pascal? How many of you say kilopascal? Kilopascal is correct. Okay, why? The reason is this. Because here we are working on kilojoule. So this pressure the unit must be in line with the right side, which is in kilo also. So we have to convert this pressure in bar to kilopascal or kilonewton per meter square. Must be in line with this kilojoule here. So 10 bar, 10 convert to kilonewton per meter square is times 10 to the power 10 to the power 5 is Pascal. Then to kilopascal, take away 3 0. Become 2. Yes, very good. Take away 3 0. So from here you can work out the mass. Okay, someone use your calculator, help me find out this figure. Sorry. 3.484 kilogram. Okay, this is the mass. This volume, at this pressure, at this temperature, the mass is this. Okay, but the mass is fixed because it's a closed system. So no matter what happens, this mass remains the same. Because it's a closed system, we are talking about a closed system process. No matter what happens, the mass is still the same. Okay, now we have the mass. We can calculate the heat transfer. So mass is 3.484. CV is 0.718. From just on the figure below, right below. 0.718, which is in kilojoule per kilogram K. T2 600 Kelvin. Then if this is Kelvin, the other side must be also Kelvin. So this one is 500 Kelvin, T1. I need to mention this is because I do come across students, sometimes maybe too rush, never check properly. One side he used Kelvin, the other side forgot the convert, he put degree C, then mistake again. Okay, so must pay attention. Okay, now with this you can calculate the heat transfer. So what do you have? 1.1. So this unit, okay, very important. Unit, what should I put? Joule, kilojoule. Kilojoule, very good. The reason is this CV, this CV here, the unit is in kilojoule per kilogram K. So that's why the answer will be in kilojoule. So this answer. So this is the first question in your tutorial. I think it's the tutorial question. First question. So let me try another question. Then this one later you can try again. Based on the tutorial question number, you try again, you should get the same answer. Okay, let me try another question. Which one you want me to try? Number 2 or number 4? Okay, why not number 3? Because number 3 is positive. So we're talking about perfect gas first. So let's try the perfect gas question. Number 4, yeah, do one more, then later you try all the 3. Okay, number 4. Okay, hang on. Still have a bit. Okay, number 4, this is 1 kilogram of air. Okay, similarly, I will change the number. So you know my style already, so let me do the way. Okay, instead of 1, I put 2 lah. Okay, 2 kilogram of air has a pressure of 1.2 bar. Instead of 1.2 bar, I change to 1.5 bar. Okay, 1.5 bar. 1.5 bar. Yeah, change it. I don't quite like the decimal point. Okay, change to 2 bar. 2 kilogram of air at 2 bar at a temperature of 30 degrees. Okay, instead of 30, I change to 27 degrees C. Okay, 2 kilogram of air at 2 bar, 37 degrees C in a cylinder. In the cylinder is compressed according to the law. What law? PV 1.25 equal to C. So what does this represent? What does this thing represent? Polytropic process. Okay, when you see an equation described this way, compressed according to the law of PV 1.25 equal to C, then take this as polytropic. And this 1.25, this is the N here. This is the N inside. If you ask me how come this is not adiabatic, okay, the answer is simple. If this is an adiabatic question, though normally I will say the question this way: 2 kilogram of air at 2 bar and 37 degrees C in the cylinder is compressed adiabatically. So I will not say this way. I will not say PV 1.4 equal to C. So seldom I do this way. So I just say compressed adiabatically. So if I say it's according to the law, PV equal to PV 1.5 or 1.3 equal to constant, take this as polytropic. And this number here is the polytropic index. Okay, now this one compressed to the pressure of 6 bar. Okay, I don't change the 6 bar, it still remains 6 bar. Now calculate the final temperature, find the work done, and the heat transfer. Okay, so this is the question. Do you need this? Have you copied down this one? If have, I wrote over there. Anyone haven't copied? Yeah. Okay, so I have a mass of 2 kilograms. Question 4. Mass 2 kilograms. And initial pressure 2 bar. P1 2 bar. And temperature 37 degrees C. 27. I changed to 27. I changed to 27, huh? Not 27, 27. So now compress according to the law PV 1.25 equal to C. PV 1.25 equal to constant. Until the pressure is 6 bar. So this 6 bar is P2. This 6 bar is P2. Huh? Now find the final temperature. Final temperature is T2. What is this T2 here? And find the work done and heat transfer. So find the work done and heat transfer. So that's the question. Okay, so let's look at the table. What we have and what we need. So this is polytropic process. Polytropic. So we look at polytropic only. So if you want to find temperature, what can you use to find temperature? You are given these two pressure, P1, P2.
MCD.
So you have pressure P1, P2 here. You also have pressure P1, P2 here, but what you need to find is temperature. So what I'm going to do is, I use this one to find my temperature. Why this one? P1, P2 given. And 1.25 also given. T1 given. Only unknown, T2. So that's why I use this one to find my temperature. So let me write here. P2 over T1 equal to P2 over P1 n minus 1 over n. So my T1 convert to Kelvin plus 273 is 300 Kelvin. T2 and T1, what units do we use? Okay, I will show you later any different or not. Show a bit dry. Okay. T2 is the unknown, huh? So this is what we want to find. T1, I shift to the right side. Shift to the right side is become multiplier. So this T1 become multiplied to the right side. T1, I shift to the right side become multiplier. Cross multiply. So now put in the number. T1 I have is 300 Kelvin. 300 times P2. Okay, now I have pressure divided by pressure. Okay, pressure divided by pressure, you can leave it as bar. If you change to kilopascal or you change to Pascal, any different, let me show you. So let's say I put to Pascal, P2 6 bar, so it's 6 times 10 to the power 5. P1 is 2 bar, so 2 times 10 to the power 5. Then N 1.25 minus 1 over N 1.25 again. So this one I mentioned pressure divided by pressure. I convert to Pascal. The 10 to the power 5 on top and 10 to the power 5 below cancel away. So end up the same. So if you leave it as bar, still okay. But only catch is make sure these two are the same unit. You cannot have bar on top, kilopascal below. Then definitely your unit is wrong. Must be the same unit. Okay, with this we can calculate T2. So what do we have? Again, what? 373.7. 372.7.
373.72.
1.72. 373.72. Okay, very good. So 373.72 Kelvin. So that's the answer. So I just leave my answer in Kelvin. Unless the question asks me convert to degree C, then I convert. Otherwise, I just leave it this way. Okay, next, I need to find the work done and the heat transfer. Okay, work done, W. Work done is W. For polytropic, I have two options. One on top, one below. Which one do you choose? Below one. Why? Mass have 2 kilograms. Given. So this one no issue. T1 have. T2 just found. T2 just found. And given. So everything have. So this one is a good option. Good choice. If you choose this one, nothing wrong. It's not saying you choose this one is wrong. Question is, if you choose this one, you have P1, you have P2. Do you have P1 and P2? Don't have. Means before you can calculate, go and find what is P1 and P2. So this is long way. Not wrong, long way. You have to go to Holland, make a big turn, then come back, then you can find the answer. Long way. Not wrong way. This is not wrong. It's long only. You need to make one big turn in order to find the answer. Okay? So this one is nothing wrong. Question is you need to find a lot of information first. So shortcut way is, since I have everything, let's use the second equation. Since I have all the items ready. Okay, so M already have 2 kilograms, R is 0.287, 0.287, T1 300, T2 373.72. So divide by N 1.25 minus 1. So what do you have? Sorry? Yeah, it's negative.
Minus
169.26. Unit is kilojoule. Okay, unit will be in kilojoule. Why kilojoule? Because this unit here, this R is in kilojoule per kilogram K. So after multiply, everything cancel, the only thing left behind is kilojoule. So you have your W. So next, heat transfer, Q. So the next one will be Q, heat transfer. So heat transfer is Q equal to delta U plus W. So W is what you calculated here. This W. How about delta U? Delta U is from here. MCD T2 minus T1. So let's find delta U first. Okay, delta U plus W. Okay, delta U is MCD T2 minus T1. So MCD T2 minus T1. So everything already have. So just put in the number and calculate. M is 2 kg. CB is 0.718.718. T2 373.72. Minus T1 300. So calculate for this value. 105.86 kilojoule. Very good. 105.86 kilojoule. So once you have delta U, you can calculate your work done. Or calculate the heat transfer, which is delta U plus W. So Q equal to delta U plus W. So where delta U is 105.86. And this is positive number. Very important, this is positive. Now my W is negative. Minus 169.26. So next you get the negative value. This one positive, this one negative. So next together. How much is it? 63.4 kilojoule. It's a negative figure. So this is a negative heat transfer, means it's a heat loss. Heat loss process. So simple example. So now I give you some time to do these 3 questions. Start from first question, then do second question, which is question 4. After you do these 2, then you go to question 2. Go back to question 2. Question 2 is what process? Constant pressure process. Okay, question 2. Constant pressure process. I give you 30 minutes. Not too long. Because this one already have. This one new. Okay, later on I will do the second part, which is the steam question. Yeah, give you some time to do this half an hour. Then we will continue on the steam portion. Especially those mountain hiking. For example, some of you maybe go to Mount Himalaya, go and hike, and go and climb up to 5,000 meters. Pressure is very low because it's very thin, the air is very thin. At the kind of pressure, air is very thin, hardly you can breathe. You need oxygen tank, definitely. Then at the kind of pressure, then you go on top of mountain, definitely you need to boil water to cook some food. Then you put a thermometer, you measure water temperature, and you realize somehow temperature no need to hit 100 degrees C, water start to boil. No need to hit 100 degrees C, and the water is still boiling. Then you think, hey, how come? The reason is pressure become lower, boiling point become lower. Pressure drop, boiling point also drop. Okay, this one will be shown in the steam table. I will show you later on. So now I'm talking about at ground level, sea level. At the sea level, the pressure is atmospheric pressure. Boiling point is 100 degrees C. So when it hit 100 degrees C, water will boil. Boil means what? Bubble will form. Bubble is more volume, right? So you push the piston. You push the piston. So it becomes a bigger volume. So when you have a steam like this, and this is what we call wet steam. Wet steam, why wet steam? Why the meaning of wet? Got wet or not so wet? Okay, the meaning of wet steam is a mixture of water and dry steam. Mixture means 1 kilogram just like this one, the mass always constant because it's a closed system. The piston sucted the atmosphere and the water and steam. So the mass always constant. So some of this 1 kilogram become dry steam. Let's say dry steam is in my example 0.3. 0.3 kilogram is dry steam. So my remaining is how many? 0.7, very good. No matter how the mixture, the total mass is always 1 kilogram. So now I have 0.3 kilogram become dry steam. That's why my dryness fraction. What is the definition of dryness fraction? You learned that from Dr. Chiu.
Wet to dry.
What's the definition? Still can recall? Forgot already. You see, after 3 weeks, 4 weeks holiday, all returned back already. So dryness fraction meaning mass of dry steam
Wet steam.
divided by total mass. Now my mass of dry steam is 0.3. My mass of dry steam 0.3. Total mass 1 kilogram. That's why my dryness fraction is 0.3. That's how you calculate the dryness fraction. And normally dryness fraction we use this symbol called X. Okay? We like to use this symbol called X. So this dryness fraction is very useful fraction because when we calculate the specific volume, we need the dryness fraction. And use X times Bg, we can get the volume. So this volume here is X times Bg. Where to get this Bg? Steam table. So very important, you must know the dryness fraction. So when you heat up the water, and now it becomes wet steam, so it's a mixture of water and steam, but you still continue heating. So what happens? More and more this water become dry steam. So let's say just now was 0.3 and 0.7. So another 1 kilogram become dry steam. So become 0.4, 0.6 and 0.4. Then slowly increase to 0.5 to 0.5. So more and more water become dry steam. Then you heat again, then 0.4, 0.6, then 0.3, 0.7. Let's say now 0.3, 0.7. More and more water become dry steam. Let's say now dryness fraction is 0.7. So means right now my mass of dry steam inside is 0.7 kilogram. 0.7 kilogram. Total mass is still 1 kilogram. That's why my dryness fraction is 0.7. So my steam 0.7 kilogram is dry steam. 0.3 kilogram is still water. And the water is in the form of water particles. So it's a mixture. So as you see a lot of smoke, actually it's not smoke, it's water particles. So it's water particles. So if you still keep on heating, means you heat, still keep on heating, some of this water will convert to dry steam, so more and more water convert to dry steam. So eventually all the waters convert to dry steam. Eventually. So all this water become dry steam already, no more water. So my dryness fraction, 1 kilogram of dry steam divided by total mass is 1 kilogram, so my dryness fraction is 1. So now my dryness fraction is 1. And this point, the steam is called dry saturated steam. Just totally dry again, no more water particles. So that's why you see I draw 2 lines. Starting from here, water, then from steam. So from here to here, very steam. So now here totally dry. Now ask you a simple question. This one sometimes some of you may guess. Just now we say water boil at 100 degrees C, so it start to boil from here. So now steam totally dry. From just now here to this top line, do you think the temperature change, increase or constant? How many things is constant? Only a few. The rest no confident. Constant. Okay, any one thing is changing, increasing. So only one. So far one. Okay, the right answer is the temperature is constant. Don't change. So when you boil the water starts to boil, form steam. So from one, just now water was 1 kilogram, right? Then some of this water become dry steam. From just now until now, temperature remain constant at 100 degrees C. This is the atmospheric pressure. So temperature remain constant. So when it start changing, after the steam totally dry, when the steam is dry, and yet you still keep on heating, then this steam becomes superheated steam. Superheated steam. When you call this superheated steam, means the temperature is more than the boiling point. And this boiling point in the steam table, you can see this symbol called TS. So what is TS? TS means saturated temperature. Saturated temperature. TS in your steam table represented by this symbol called TS, which is the saturated temperature. So when it's more than saturated temperature means superheated steam, temperature is more than 100 degrees C. Then how about X? No more X anymore. Superheated steam, you cannot use dryness fraction. Okay, so that's why dryness fraction is only for wet steam. And dryness fraction is always between 0 to 1. Cannot be less than 0. Doesn't make sense. Dryness fraction less than 0 doesn't make sense. Dryness fraction more than 1 also doesn't make sense. Why? 1 kilogram of water produce 1.1 kilogram of steam. If you can do that, show me. So you become a genius. Okay? So it's impossible. 1 kilogram of water can only produce 1 kilogram of dry steam. If you say, yeah, I keep on heating, but you keep on heating doesn't mean the mass of the steam will become more. It's still 1 kilogram, but now becomes superheated steam. It's no longer wet steam, superheated steam. Okay, so it becomes superheated steam, temperature is more. So this case I only talk about volume. So let's put in another two thermal properties into the pictures. Just now I only talk about volume, volume aspect. You can see, because volume you can see easily. Now I'm going to talk about another two more properties, which is enthalpy and internal energy. These two are very commonly used in your calculation. Okay, so when you heat up the water and the water hit boiling point means the steam is still no steam yet, still 0 and 1 kilogram of water and 0 kilogram of steam, but the water starts boiling. At this point, this is what we call saturated water when it reaches boiling point. And the properties are all the F. So you can see volume is VF. For enthalpy is HF, all the F. For internal energy, UF. So VF, HF, UF. Where can you see these figures? In your steam table. In case you are not aware, let me show you. Okay, you can see this steam table, the one that you have, I zoom it in a bit. Okay, you see saturated water and steam, huh? The first column is what? Pressure. The second column is TS, saturated temperature. So this is your boiling point. So just what I mentioned, when your pressure is 1 bar, which is something like atmospheric pressure, 1 bar, which is here, quite below. You can see your temperature is 99.7. How come not 100? Because our pressure, atmospheric pressure is 101.3. 1.013. So if you calculate 1.013, you'll get 100 here. But now it's 1, so you see 99.7. So that's why I mentioned, if you climb high mountain, pressure drops. You see the pressure drop, you see your temperature also drop. That's why higher in the mountain, when you cook, when you boil water, let's say your pressure drop to 0.5 bar, which is quite thin, not easy to breathe. Your boiling temperature is only 81.4 degrees C. So it means you put a thermometer, when your temperature reaches 81.4, water starts to form bubble. Means boiling. Okay? So next, HF and UF, just I mentioned. So where do you find these two figures? Over here. HF and UF. These are the figures here. Let's just come back. So HF, UF. So now you have water at boiling point. So now you form the steam already. So 1 kilogram of water, let's say the next point is 0.4, if I don't know. You form water, 0.3. Let's say 0.3 kilogram of steam formed already. So you left remaining of 0.7 kilogram of water. So at this point, this is a wet steam. Wet steam, so to calculate the property of BF, how to calculate? So the formula is X times Vg. Use X times Vg. This is given also in your formula sheet. But for enthalpy, what do you use? You use this calculation. Okay, how to explain this? Okay, the thing is like this. This point is HF. I want to add this value inside this point, this value. And this value is X times HFG. So this plus this becomes the enthalpy at this point. For internal energy is UF plus X UG minus UF, or sometimes you just simply use UFG. So in case you wonder what is UFG and what is UG minus UF, UG minus UF actually is equal to UFG. If you don't believe me, you go inside your steam table, you just pick any one. You just pick any one. This is UFG. You use this one, minus this one, you get this value. You use this one, minus this one, you get this value. Okay, so this is the meaning of UFG. The same for HFG also. You use HG minus HF, you get this value. You use this one minus this one, you get this value. Okay, so this is the meaning of UFG and HFG. So this is wet steam. So when you heat further, the steam will totally dry eventually. So if you heat further, the steam will totally dry. So dry steam, just what I say, dry steam, dryness fraction is 1. So dry steam means 0 water, 1.0 kilogram of dry steam. So the dryness fraction is 1. So dry steam, the properties are all the G. So you have Vg, Hg, and Ug. Okay, all the G value, the value of the properties like V is Vg, H will be Hg, U will be Ug. So that's why I call this line all the G line, all the G points. Vg, Ug, Hg. Easy for you to remember. all the G. The left side is all the F. Why I need to use this is because later on, next chapter, when we talk about another properties come into the pictures, then easy for you to visualize. In fact, you also need this for your engine thermal. Every Thursday, Mr. Lim will cover this thing called the nozzle. When you cover nozzle, then you need to understand. Steam nozzle. Okay, so when you heat further, the steam becomes superheated steam, the volume will be much expanded. This point you will see like it's shifted to the right side. But then, calculating of this point, cannot use this one anymore. Cannot use this one anymore. So you have to use the superheated steam table. Superheated steam table makes one. I show you. Okay, this is the superheated steam table. Superheated steam. First column, pressure. Then the top row, the temperature, superheated steam temperature. So you want to find the value, go to the pressure, SI5 bar, and go to the temperature and read the figures. Okay, so this is how you do you obtain the value. The first is I will use an example to illustrate how I get the value from the steam table later on. Okay, so I come back to the explanation. So in summary, saturated water is all the F. So you see DF, UF, HF. There's one more S. This one, for the time being, you just ignore. Because we're going to use this one in your chapter 2. So for the time being, just ignore. For wet steam, dryness fraction is always between 0 to 1. From 0 to 1. So to get the specific volume, use X sub Vg. To get the internal energy, UM plus X UFG. To get the enthalpy, HM plus X HFG. So this one is for chapter 2. So I'll skip this one. Then for dry steam, all the G value, Vg, Ug, Hg. So this value will be larger than this value. This value also larger than this value. Okay, so this is always in between UF or between the F value and the G value. So wet steam value, is always between the F value and the G value. Always between this. Because the F value is all X is equal to 0. The G value is X equal to 1. So the wet steam is between 0 and 1. So it's in between these two. In between these two. So if let's say you say, I have a value more than Vg or I have a value more than Ug, then how? That will be superheated steam. The superheated steam value will be more than all the G value. So the V will be more than Vg, U will be more than Ug, H will be more than Hg. Okay? Okay, next I want to talk about interpolation. I think most of you, after 3 weeks holiday, 4 weeks holiday, this part, if you seldom use, forget it. Okay, interpolation is useful when you need to get a value between 2 points. But your point is in the middle. Your point is in the middle. I want to get a value here. How do I get? Use this interpolation equation. So how to apply this interpolation equation? You just need to identify what is your x1, what is your x2. You have an x value. I want to find my y. I want to find my y value based on these two y1 and y2. This example. So in your steam table, I want to find the enthalpy at 60 bar 370 degrees. So you look at the steam table, 60 bar 370 degrees. Cannot find. Why? Because your steam table only have 350 and 400. So you look at the steam table, you look at the temperature, only 350 and 400. So then how? You have to do interpolation in this case. So how to do interpolation? So I look between these two temperatures, 350 and 400. At 350, I get a value. At 350, I get this value of enthalpy. At 400 degrees C, I get another value. Then, what I want is 370 is between these two. So I do an interpolation using this formula. I can work out at this 370, what is my Y value here, which is the enthalpy at 370 degrees. So this is how we apply the interpolation. Any question on this one? This one will be, we'll use it later on. Okay, for calculating of steam, just now I say you cannot use the perfect gas equation. You cannot use this one anymore. This one cannot use for steam. But then you say, if I want to calculate the work done, I want to calculate the heat transfer, what can you do? You can use this table. So this table calculates the work done and heat transfer for closed system of steam process. Closed system, I don't think no. Per kilogram of steam means per kilogram of steam. This is specific work done, specific heat transfer. Specific. So to illustrate this, I use one example. Let me use one example to explain. Okay, in your tutorial question, let me use one question and explain. I will use question 3. Question 3. Okay, I use question 3 to explain. Okay, question 3 is this. I have 1 kilogram. Okay, same thing. I cannot just simply follow this, then I get the answer. You just copy. Then you never do again. So what I will do is I change the number. So what number I change? I don't show you. Okay, still 1 kilogram. This one I don't change. 1 kilogram of steam at a pressure of 15 bar. 15 bar. And the temperature of 300 degrees C. Instead of 250, I change to 300. So 15 bar, 300 degrees C. Cool at so heat loss. Cool at constant volume. Constant volume is what you know, constant volume. Don't change the volume. To a pressure of, instead of 4 bar, I change to 5 bar. So from 15 bar, 300 degrees C, cool down to 5 bar. So find the final condition. So what does it mean? This point 2 at 5 bar, what is the condition of the steam? Is it a wet steam? Is it a superheated steam? If let's say this is a wet steam, what is the dryness fraction? If this is superheated steam, what is the superheated temperature? So if this is a wet steam, what is the dryness fraction? If this is a superheated steam, what is the temperature? So the answer you see here, this is not temperature. So this is dryness fraction. So means the final answer is the wet steam. Okay, but now I change the number. We don't know the answer yet. I change the number already. Then find the heat transfer. Heat transfer is Q. Remember, heat transfer is Q. Okay, the answer is in kilojoule, so heat transfer is Q. So what is Q? Q is equal to, okay, let me show you this again. Remember this? This is small q. This is small q. For constant volume process, the Q is equal to U2 minus U1. So for constant volume process, Q equal to U2 minus U1. Then what is Q? Q is capital Q divided by mass. Because this answer is per kilogram of steam. This one, the calculation is per kilogram of steam. Now we want to find capital Q. Capital Q. So it's equal to M times Q. Yes, very good. Which is equal to M times U2 minus U1. From here. Okay. So, meaning to say, to find this answer, we need to find U2 and U1. Okay, so how to find? Step by step. Let me show you the step. So this part we did already. So let's go back to the question again. So let's do the solution here. Question 3. This is a constant volume process. My mass is 1 kilogram. This is M. M equal to 1 kilogram. This is the mass. So my pressure is 15 bar. Just like I mentioned, 15 bar. So my point 1. Point 1 is the original condition. My pressure is 15 bar. My temperature is just now I use 300 degrees C. So this is my first point. Then my point 2, my pressure dropped to 5 bar. But condition we don't know. Condition we don't know yet. So what can we do? Okay, let's look at the question. So it says that this is constant volume. Constant volume means what? Volume constant, no change. No change. So if constant volume no change, you divide by mass. Divide by mass, divide by M, divide by M. You get specific volume. Right? Capital B divided by M, you get small b. Capital B divided by M, you get small b. So is the specific volume also the same? So what does it mean? If you find your specific volume at point 1, this value also the same as point 2. Same volume, specific volume. If you cannot understand, one more time, volume normally is in meter cube. We normally use meter cube. For steam, we use meter cube. But in the steam table, the specific volume is normally used. The specific volume, the unit is meter cube per kilogram of steam. This is the unit. Because you divide by M, you divide by kilogram, you divide by mass. That's why you get meter cube per kilogram. So what we need to do now is we find B1. And this B1 is the same as B2, the specific volume. So B1 is what temperature? 300 degrees C, 15 bar. This is a superheated steam. How do we do? Okay, very simple. We just go to the steam table. Go to the steam table. Look at 15 bar. Okay, I show you two sides so that you can follow up. First of all, I show you the saturated water and steam. Okay, first one, I show you this saturated water and steam. Then you look at this first column, 15 bar, which is below. 15 bar is here, below. Then you look at the second column, this is TS, which is a saturated temperature. What is the temperature here? 198.4. 198.4. This is TS. So, the temperature 300 degrees C given is far higher than 198.4. Higher. So, what does it mean? Superheated steam. Remember this one I mentioned before? This one? That's why I need to report. I need to go back and forth so that we can relate. That's why I mentioned now my steam is here. The temperature from here to here no change. Now I have a temperature more than this point. This more than the temperature already, more than TS. So means superheated steam. My temperature is more than the TS. So it's superheated steam. Okay, so then next we know it's superheated steam, then what? Okay, we go to the superheated steam table already. So once we know it's superheated steam, we go straight to the superheated steam table. You can see superheated steam. Then look up for 15 bar. Now my pressure I change to 15 bar. 15. Then look at 300 degrees. 300 degrees. 300 degrees. Then 15 bar. Then look for V. This is the volume. This is the one. Okay, 15 bar. Okay, below 15 bar you can see this 198.4. So this is what? TS. Just to remind you, this temperature, the saturated temperature is 198.4, which is this one. Just a reminder again. So now we look for V. This is 0.1697. So V 0.1697. Unit is meter cube per kilogram. Meter cube per kilogram. Now V1 and V2 is the same. Also 0.191697. 1697. But my V2, the pressure now is 5 bar, not 15 bar anymore. Now it's 5 bar. We are talking about 0.2. Now I have the volume, specific volume of 1697, 0.1697 at 5 bar. How do I know what's the condition? How do I know what's the condition? So we go back to the concept we just learned. Okay, this one actually you learned before, just that relearn in case you forget. Still remember this one I just mentioned? So if you are resting, your volume will be between this value and this value. Okay, I pulled out the line so that you can see. If you have a resting, this volume will be between this and this value. If your steam is superheated, then this volume will be more than Vg. So your common reference is this Vg. If I have a volume and I check versus the Vg, if this is more than Vg, then I know this is superheated steam. If I have a volume and I compare to Vg and found that it's less than Vg, then I know it's a wet steam. So this is how I check. This is the reference. So Vg, this dry saturated steam, this x equal to 1, this Vg is my reference. Okay, so I check versus the Vg. Check versus the Vg. So Vg at 5 bar, not 15 bar. I'm talking about 0.2 now. 5 bar. So let's look at Vg at 5 bar. So VG and 5 bar, you can find from these two locations. I said two locations. One is from superheated steam, this location. You can see this pressure on the first column. The second column are all the G value. Second column, all the G value. VG, UG, HG. And one more G, SG you'll use in chapter 2. Okay, so here you can see your VG here. So this is first place you can find. Okay, let me write it down first. 0.3749. This is the first place you can find. Second place you can find this VG is at the saturated water and steam. Saturated water and steam. So you look at the third column, you can see VG. Third column. So look at 5 bar. 5 bar VG 0.3749, same value. So this is the second place you can find. Okay, so two places you can find the VG or the G value. So I have this VG and I have this V2. Is it less or more? This one is more than B, or B is less than VG. So now this is less than VG. So which case this one belongs to?
1.6.
Less. This is more than VG or this is less than VG?
More than VG. This one is
Less than VG. So less than VG is what? Resting. So less than VG, resting. Less than VG, resting. Under this case. Under this case. This is less than this one. So now resting, yes. So at least you confirm one thing, it's resting. Next, what is the dryness fraction? How to find the dryness fraction? Remember just how I said, if this is super resting, this you need to find the temperature. If this is resting, you need to find the dryness fraction. So how to find the dryness fraction? We will use exactly this resting calculation. Where this is your value, this is your V2. So V2 equal to X times VG. V2 equal to X times VG. So this X is the dryness fraction. This V2 is this value here. This value. This VG is this VG value here. So you have this V2, you have this VG, only unknown is X. So can find out. Can find out. So V2 is 0.1697. X is my unknown, the dryness fraction. VG 0.3749. So what is my X? 453. So my answer will be the steam is the wet steam and the dryness fraction is 0.453. So this is how we answer the question. Steam at point 2 is the wet steam and cannot full stop. You full stop means you only half correct. You want to completely correct, you have to answer also what is the dryness fraction. So the dryness fraction is 0.453. So this is only the first part. So the second part they say calculate the heat transfer. This one, just one I mentioned. Heat transfer, this is Q. Q equal to M times small q, which is U2 minus U1. So you need to find U2 and U1. Okay, U1 is 0.1. U1 is 0.1. U1 is 0.1, then U2 is 0.2. Okay, let's find U1 first. U1 at 15 bar, 300 degrees C. U1 at 15 bar, 300 degrees C. Okay, U1 at 15 bar. Super testing, huh? I'm talking about super testing here. Super testing. 15 bar, 300 degrees C. Look for U. So this is the value. Look for U, 300. Okay, correct. So it's 2783.1. 2783.1. Kilojoule per kilogram. Two 783.1 from here. Super testing. 300 degrees C. So this is 0.1 super testing. 15 bar, 300 degrees C. So U1 settled. Next, U2. Next, find U2. U2 is superheat, is a vesting. So U2 is a vesting. Remember this one? Vesting. Vesting for U. Vesting is UF plus X UFG. So U2 is UF plus X UFG. It's a vesting, right? So UF plus X UFG. X is the dryness fraction we found here. The X is this one, this value. How about UF and UFG from steam tables? You go to the steam table. This time round, this is a wet steam. This is a wet steam. So you go to saturated water and steam. Saturated water and steam. Okay, not superheated steam. Saturated water and steam. You go to superheated steam. You also cannot find UFG. The only place you can find UFG is here, in the saturated water and steam. So you look at 5 bar. Then you can see UF and UFG, which is 640 and 1921. UF and UFG is two values. So you get these two values here. 640 plus 0.453 times UFG, which is 1921.
Okay, different question now. You doing this question or only the question?
Can someone help me get this value? 1.10.21 kilojoule per kilogram. So I have my U2 already. I have my U1, I have my U2. I can calculate my heat transfer. Okay, I do it here since I write the equation here. So the heat transfer equals to M times Q, which is M times U2 minus U1. My M is 1 kilogram. 1. My U2, 1.10.21. 1.10.21. My U1 is 2783.1. 2783.1. So you calculate what you have is negative. 1272.
U.
Point 89
KH.
kilojoule. That will be the answer. Okay, so I stop at here. I'll let you try again this question. This one quite challenging, I know. Try again. Try this question. And finish, call it a day. We will continue on Wednesday.